a very, very, very brief presentation. I like to introduce Moritz Lehmann. It's very young, but very expert about OpenCL. If I'm not correct, he has spent the last 5 years working on the code. I'm correct, Moritz?
Yeah.
Okay. And as a very short bio that he sent me, let me check. Okay. Simply is from Bavaria, Germania. He got recently a PhD in physics at the University of Beirut. It's right, the pronunciation, or
Bayreuth. Not
Bayreuth.
not to miss Beirut and Beirut. It's different cities.
Yep. Sorry for that, but German is not my usual easy language for me. And he was main developer of the open source code Fluid X3D. That's you can see sometime on web, on YouTube, with a very colorful picture of flow around from airplane to jet and even Star Wars machine.
A small correction. It's source available, not open source. A small difference.
Sorry.
To clarify.
Yes, you're right. You're right. And he got his PhD working about a microplastic problem, so a biological problem here with microplastic and water and their interaction. I think as a brief introduction is enough. So Moritz, the floor is yours. Please, for all the attendees, to mute the microphone because we'll be supposed to be quite big numbers, so noise could give some distraction. So the floor is yours.
Thank you, Giorgio, for the invitation here and also for introducing me. So I am Dr. Moritz Lehmann. Today I will present to you OpenCL GPU programming for high-performance computing applications. This will be sort of an introduction to the topic. In some points I will just skim the surface, and in some other points I will go into more details to keep it also friendly for beginners. Okay, so I start with a brief introduction about me. In my teenage years, I was very much enjoying playing the violin in the school orchestra. In 2015, I made Abitur at Gymnasium Münchberg. Then I got very excited about physics, and I did a bachelor's degree in physics at the University of Bayreuth, followed by a master's degree, whereby I compressed it down and listened to part of the lectures already in the bachelor, so I could do it in 1 year only. I followed up with a PhD. It was actually summer, and I finished just at age 25 still. And this is also what got me into high performance computing. Here's an image of me installing one of the A100 GPUs in our data center at university. To fill this large gap in my CV that you see, I also finished the Elite Study Program Biological Physics at the Elite Network in Bavaria in 2022 with top grade actually. And I also finished the graduate program of the German Aerospace Center. To round things up, I did a postdoc up to the present day. And now I can enjoy my life again. So as for today, I'm open for industry positions. But this is only half side of my life, because I'm actually sort of living a double life. On daytime, I'm doing career stuff, and at nighttime, I'm a programmer. So starting 9 years ago, 2014, I taught myself Java programming with the Physics 3D N-body simulation software. Here, this is an image of the software with the orbits of the inner planets and the asteroids in the asteroid belt. Visualized, I implemented the entire graphics engine in Java back in the day. In 2016, I started with OpenCL programming. In 2017, I then transitioned from Java and OpenCL back in the day with the Aparapi interface to C++ and OpenCL. And then I wrote Fluidics 3D software. I had this crazy idea to write my own computational fluid dynamics software from scratch. So that's what I did for 4 years. And in 2022, I decided it's time for a complete rewrite of the software to make the code much more clean and readable and also optimized. So that's what I did. Half a year later, I released the software on GitHub in version 1. Today, the source code has 2,000 stars on GitHub already in version 2.8. And in the meantime, I also joined the OpenCL advisory panel at the Kronos Group. So what is this software? Here's an image of it, a simulation 10 billion cells in ½ terabyte of VRAM on a single GPU node. Competing commercial software would take about 18 months for such a high detailed simulation. And this takes about 10,000 euros in electricity cost. And with my software, I do it in an afternoon just for fun because I can. And that's what makes people really excited about the software. So here's the GitHub page on it. And about 1/3 of the code, all of the heavy lifting is done in OpenCL. So this is the entire GPU part. The CPU part is in C++, and it's for sort of managing the structure of the software and the user interface and everything else. It has gotten very popular over the last year. Here's some of the other excellent, very popular open source codes, and you can see that the popularity of Fluidics 3D is really going through the roof. As for today, on the rankings, GitHub topics, I am number 2 in CFD. Number 1 is the very popular CFD Python course by the Barber Group. So I can say that Fluidics 3D is now the most popular CFD software on GitHub. In the HPC, high performance computing category, I'm in ranking number 9. And in OpenCL, I'm in ranking number 12 already. And I did all of this solo. Now let's talk about OpenCL, a bit on the history of the language. In 2009, Apple was actually the company who released it. And it was later transferred to the Kronos Group. In 2010 came OpenCL 1.1. This came with a lot of improvements, especially more math functionality. In 2011, OpenCL 1.2 was released. This is the language standard still to this day and is compatible across all hardware. From 2013 to 2017, the OpenCL 2.x standards got released. They have some very nice extensions that have been included in these 2.x standards. The most notable are shared virtual memory, more subgroup functionality, and the OpenCL C++ language. But in 2020, OpenCL 3.0 was released, and this is mostly a rebranding of OpenCL 1.2, making all of the OpenCL 2.0 features optional. Now, starting with the big advantages of OpenCL upfront. So OpenCL is the open industry standard for GPU computing. And the biggest advantage is that it is compatible with literally all hardware out of the box. This includes all GPUs from all vendors, including AMD, Intel, Nvidia, ARM, Apple, and even some of the new Chinese manufacturers like Glenfly. This includes gaming, workstation, data center, and also the integrated GPU, so no discrimination between the GPU segments at all. And it also runs on all modern CPUs, including AMD and Intel CPUs, and also Intel Xeon Phi CPUs. It also runs on FPGAs and accelerators. The performance of OpenCL is exactly the same as CUDA. There's no performance disadvantage whatsoever. That is a myth that has spread over the past years, but that is not true, and I will show this later. And lastly, you can optimize your GPU code for one GPU, and at the same time, you optimize it for all GPUs and there's no porting required. You can deploy the very same software on the new supercomputer if the new supercomputer has GPUs from a different vendor. Now we're seeing the very large supercomputers with the AMD Instinct GPUs, but at the same time also the new Intel Sapphire Rapids CPUs. And of course, the Nvidia GPUs are also very popular. To give an example, the Fluidix 3D software, I have benchmarked it across a large variety of hardware. At the top, there's the AMD Instinct accelerators, then the Nvidia data center GPUs, and then all of the gaming GPUs, AMD, Intel, and Nvidia, and further down some of the Sapphire Rapids Intel CPUs even. Also, it runs also on the Apple silicon, which is very nice. So now going on with continuing with a comparison between CPU and GPUs, what are the differences between the hardware? Here I've illustrated examples of both the i7-8700K and the Titan XP GPU. This is the hardware that I'm using in my PC currently. On the CPU, there's few cores, few with an asterisk, because nowadays it's up to 128 cores with the newest AMD CPUs, and each of them typically has an 8-way SIMD unit. So SIMD is single instruction multiple data. So in a single clock cycle, a CPU core can compute 8 elements, 8 32-bit floating point elements of a vector at the same time. On the GPU, there's so-called compute units, in short CUs, and the number varies greatly between models. So on the old toaster GPUs, it's only 2 compute units. On the newest Nvidia Ada Lovelace GPUs, it's up to 142 compute units. And each of these compute units typically has a 128-way SIMD unit. So each of them contains 128 CUDA cores or stream processors. And the number of stream processors per CU also varies between the GPU architecture. So it's different. For some, it's only 64. For some, it's 128. For some, it's 192. The main difference between the two is nowadays not the compute units themselves, because also the CPUs are going in the SIMD direction, and on the GPU side, the CUs can compute independently. For example, branching, they do completely independently. The main difference is the memory bandwidth and capacity. So the CPU has very slow memory bandwidth, nowadays between 20 and 200 gigabytes per second. And on GPUs, it's about an order of magnitude faster, between 500 and 2000 gigabytes per second. On the other hand, the memory capacity on GPUs is typically much larger, between 16 gigabytes and 12 terabytes for the large multi-socket server CPU systems. This is because you can plug in the memory modules as extensions on the main board, and on the GPU you can't do it. It's soldered to the PCB of the GPU. So GPUs have typically a rather small memory capacity, between 2 and 192 gigabytes. The 192 was the lately released AMD MI300X GPU, which has all of the memory as high bandwidth memory directly next to the chip, which is really impressive. Yeah, OpenCL runs on both of these hardware types, which is very nice. Now to the memory model. So OpenCL has 5 different memory types. Here I have visualized the host and the device side. So the host side is typically the CPU with the system RAM, and the device side is typically the GPU with video memory, but the device can also be another CPU or the same CPU itself. So the system memory down at the bottom here, this is host, known as host memory in the OpenCL memory model. The VRAM is known as global memory in the memory model. The GPU itself has cores, and each of these cores has private memory. And the cores are grouped in compute units, and across compute units, there is shared local memory, and all of the cores can access the local memory. The GPU itself also has a cache, and this can be used as so-called constant memory. For example, for lookup tables, if the lookup tables are really large, they might not fit in constant memory anymore and are in part or entirely also stored in VRAM. On the hardware side, the RAM for the CPU is nowadays the double data rate memory. The newest revision is DDR5. On the GPU side, it's either HBM or GDDR memory, nowadays GDDR6 or 6X memory. The constant memory is the L2 cache. The local memory is the L1 cache, and the private memory is the registers. The registers are the fastest to access. L1 cache is a bit slower, L2 cache even more slow, and the VRAM is the slowest to access. Now let's look at the structure of the platform, device, context, and program for the C++ API for OpenCL. So all of the devices are grouped into platforms, and each platform corresponds to one device vendor, for example, the GPU vendors. So here's 4 devices for GPU vendor 0. This might be Nvidia GPUs, for example, and 1 GPU for device vendor 1, which might be an integrated Intel GPU. Within these platforms, there's so-called contexts. So these allow sharing resources between devices, and you can group several devices within a platform in a context, but you cannot share the context across platforms. Within each context, there's the program object, so you can share the same program between devices, but this also only works within a context. A simplified variant of this is to encapsulate every device in its own program and context. And I can simplify this even further by just putting all of the devices in one vector of devices. This is what I'm using for all of my OpenCL projects, and I have made a wrapper around the C++ API. This is available open source on GitHub, and this greatly simplifies things. Why do I want to do these simplifications? Isn't it beneficial to share a context across devices? The idea for this shared context is to be able to ideally copy data directly between GPUs in a peer-to-peer fashion. However, the peer-to-peer and remote direct memory access, so the data copying between GPUs directly within the same OpenCL context, it's broken for all GPU vendors. So Nvidia keeps it proprietary to CUDA. Congratulations. For AMD, the peer-to-peer API call, so they have it, the functionality in the API, but the API call seg falls deep in the driver. For Intel, it works between the CPU and the iGPU, which is very nice, but not currently between Arc GPUs, and I have not yet tested Sapphire Rapids, but I'm excited to try it out. On top, if you share context between devices, it occupies about 150 megabyte of video memory, even on the unused devices. So if you think I'm doing this smart and I just put all of the devices of the same platform in the same context and only use 1 or 2 of them, then all of the others have about 150 megabyte video memory occupied. And to other users of the server, it might look like the GPUs are in use by you, so they are blocked for other users. So this might create issues. So right now, there's not really benefits to sharing the context, and it's much less boilerplate code to the developer. I've made this wrapper to significantly ease using the C++ API with this simplification. All right, now to the code structure. So I've put a big bar between C++ and C and OpenCL C because the 2 languages are really separated in the code. So the CPU code and the GPU code are completely separate. The OpenCL C code is compiled at runtime, and this is what enables this great compatibility across devices and also the portability. There's two options for including the GPU code. The first one is to load the OpenCL C code at runtime from a separate file, usually with the .cl extension. This has the disadvantage that the executable itself is not portable, so you cannot copy the executable around. It always needs the CL file in the same relative directory. However, you get nice syntax highlighting in the editor, which makes working with the code a lot easier. Another difficulty is that if you want to do macros in the OpenCL part and you want to transfer the macros from C++ to OpenCL, you have to embed them in the OpenCL C string. As a different option, you can embed the entire OpenCL code string in the executable, which means that the executable becomes portable, and you can retain the nice syntax highlighting with an evil stringification macro. So this is a C++ macro, and everything that you put in the brackets of the macro will retain the text highlighting in the editor, but it gets converted to a string by the compiler. So this is a really nice trick to sort of have the benefits of the syntax highlighting and the benefits of embedding the OpenCL code in the executable directly. Now, what is this OpenCL C language? This is the language that you program the GPU with, and this is the part that actually runs on the GPU. So it is based on C99, which is a really nice language standard, my favorite language. And it has additional integrated math and vector functionality. So very similar to the C++ standard math library. All of the trigonometry and other mathematical functions are included, and you get vector support for 2, 3, 4, and even 16 component vectors. And you can use all of the math functionality with these vectors, which makes it really nice to work with. Now you can also use the local and shared memory, which is the L1 cache. You can use that manually to optimize your code, and that gives you great control about performance optimization. On the other side, there's certain restrictions because GPUs are a bit more limited in their computing capabilities than CPUs. So the code structure also has to be more simplified. These include that you can only work with one-dimensional global arrays. There's no dynamic allocation, so you cannot just make a new array in the code. You have to pass it over as a kernel parameter. You cannot do recursion in OpenCL, so everything has to be done in loops. There's no global variables that you can sort of share across functions, except for constants. They are useful for example, lookup tables. You can use structs in OpenCL, but there's no classes and also no inheritance and interfaces and dynamic polymorphism and all of that. So none of that is available in OpenCL. And you cannot put local or shared variables in functions, so they can only be directly in the kernel. Now, a simple example of an OpenCL kernel, so that you don't have to be afraid of the language. So how it looks like, it looks just like a function with a void return type and the kernel keyword in front. It has input parameters. They are marked with the global keyword, which means that they are buffers that are residing in video memory. And A and B are additionally made const, which means that as a programmer, you cannot change these. And they are of data type float. Now, in the first line, you get the loop or thread index. So the entire kernel is like the inner part of a C++ loop, and it only executes one iteration of the entire loop. And to get the loop or thread index, you call this get global ID function. And with this thread index, you can then access the arrays and do an addition of the vectors for only one element and store the result in C. So this is a vector addition example. And all of the iterations, all of the thread indices are computed in parallel. And each one is run with a single GPU thread, and GPUs nowadays have like 18,000 cores, so they can do 18,000 of these threads in parallel, and that's what makes it really fast. The number of iterations is set on the C++ side as a kernel range. And the kernel range can really be in the billions. So it can be a gigantic number and the GPU scheduler just handles it, no problem. You can also use functions in OpenCL. So this is just an example for a simple function. Doesn't really make sense in this case, but you can abstract parts of code in functions and call the functions from the kernel. And you can pass the local and also the global parameters through functions. Typically, functions almost always get inlined by the compiler, which means that the inner part of the function is copied directly into the kernel where it is called. This lengthens the assembly code, but it reduces the overhead for the function call itself. Now the C++ API, how it works is that the CPU enqueues GPU commands. So the CPU tells the GPU what to do, and all of the commands are put into a queue. There's 4 main commands that you can do. One is the enqueue read buffer, so that reads data from the GPU and copies it into CPU memory. There's the enqueue ND-range kernel. This executes the kernel. There's the enqueue write buffer function, which writes data from the CPU side to the GPU video memory. And then there's the queue finish, so you can finish the queue. The memory commands, they can be either non-blocking or blocking, which means if they are blocking, that the CPU waits on this command until it is finished. If it is non-blocking, the CPU can just continue with the code until it hits a blocking command in the queue. The kernel always is non-blocking and the queue finish always is blocking. So as an example, you can use all of these non-blocking and then do queue finish. So the CPU goes directly, almost instantly to the finish command. And at the finish command, it waits until the GPU is really finished with the computation and the data transfer is also done. Now, a very important thing in GPU programming in general and also in OpenCL is the coalesced and misaligned memory access. Coalesced access, what is it? So you have your threads in your work group in private, and each one of them has their private memory. And you have memory cells in global memory. And when consecutive threads access consecutive memory locations, then you have the coalesced memory access. The compiler notices this and can do optimizations on the memory transfer. And this is what makes the memory transfer really efficient. The common way to do it is the structure of arrays data layout. So if you put your data in this structure of arrays layout, you almost always get coalesced memory access. This achieves up to 100% of the theoretical VRAM bandwidth, so you can really get on the hardware limit itself. Now, sometimes the world isn't nice and you cannot do coalesced access every time. And if the access is somehow different from consecutive threads accessing consecutive memory locations, then it is misaligned memory access. This happens for unordered or even strided memory access, or even random memory access if you access the memory locations through a lookup table. And this will greatly reduce performance. An example of it is the array of structures data layout, which leads to misaligned memory access. So the performance penalty can be as large as 5 times compared to coalesced access, which is really a lot. And the penalty is especially large for misaligned writes. So writing data in VRAM is a lot slower in misaligned. As in a few examples, here I've done hardware benchmarks on the memory access bandwidth for the different access types. You see, for example, for the RTX 3090, for the reading access, which is direct pillars, it doesn't make a lot of difference if it's coalesced or misaligned. However, for the writing access, only the coalesced writing is very efficient, but the misaligned writing is very slow in comparison. And this is the case across the board for almost all of the GPU models. For some, it's a bit different. For example, the AMD GPUs, somehow the misaligned reading access is, it can be faster than the coalesced reading access, which is very peculiar. Now, branching in OpenCL, you might all have heard that branching on a GPU is very bad, but it isn't as simple as that. Actually, it depends. So the compute units can all branch individually. And typically nowadays, there's only between 8 and 192 threads per compute unit. And each of them can do a branching individually. So one compute unit can do one branch and another one can do a completely different branch independently. Within a compute unit, this is where it gets difficult, because within the compute unit, no branching works. And if only one of the threads executes the slower of the two branches, then the entire compute unit has to execute the fast and the slow branch, and this increases the runtime of this single work group, and it leads to a performance penalty eventually. However, there can actually be a speed up if you know that the probability is very high that all of the threads within a workgroup execute the same fast branch. And statistically, the probability is low that any of the threads accesses the slow branch, then there will actually be a speed up. A useful example for the speed up is guard clauses. So at the very beginning of a kernel, you can make a so-called guard clause, so an if condition, that the only thing it does is a return. So the kernel stops immediately if the condition is met. The best example for this is a check on the global ID, which means if you have data that is larger, or if the range of the kernel is larger than the array has elements, you don't want to access the elements that are out of bounds. This can actually crash the program. And with a simple guard clause, you can avoid this. Now, the erase condition. This is a mostly GPU specific bug. Here with an attention sign, because it's a really bad bug for GPU programming, and it can make the GPU programming very hard. There's two variants of this bug. So the first is when two or even more threads write different values into the same memory cell at the same time. And because kernels are executed in parallel, the order of execution of the threads is random. And the last thread who writes his value last into the memory cell wins. And this is the memory that this is the value that you will then later find in the cell. But whoever is last in the race is completely random, and that's why it is called a race condition. The second variant is that when a thread reads a memory location while a different thread writes a value to the same memory location. So the value that the reading thread gets can then either be the old value or the new value, depending on if the other thread has finished or not. And this also is completely random, and it is the same race condition bug. How to spot these? If you run the software, if you run the program twice and you get different results. So if the simulation, for example, is non-deterministic, then you know for sure that you have a race condition bug in the code and you need to fix it. The only exception is if you use atomic floating point addition. So there's these atomic addition commands which allow you to add floating point numbers to the same memory cell, and while one thread is accessing the cell, it blocks the access for the other threads, so none of the values get lost in the summation. However, the order of addition still is random, and because the round of error of floating point depends on the order of the arguments in the equation, the round of error can change. So the result is still physically correct and also mathematically correct, but the round of error is random. And this also makes the simulation results random. And once again, really attention, this is a really nasty bug, and this can cause a lot of trouble and weeks of debugging. Now on the performance model, how to find out the performance of a kernel and especially how efficient a kernel runs. Here, this is an example where I pass an array of 3D vectors and I pass an array of results. And all the kernel does is for each of the vectors, it computes the length of the vector. So by squaring all of the elements, summing them and performing the square root and writing back to the results. And yeah, in this you can easily just visually spot how many floating point operations there are. So there are 6 floating point operations. The square root also is only 1 operation. And there's 2 integer operations for the index computing. You might notice there's this 2 times def underscore n, which is also a multiplication, but def n is a macro, so just a constant, and different constants will already get computed together by the compiler, so this is not a multiplication at runtime. So in total 8 operations. For the memory access, 12 bytes are loaded and 4 bytes are stored. So each of the vector elements that is loaded is 4 bytes loading, and the result is 4 bytes in storing. So in total 16 bytes of memory transfer. Now you compute the so-called arithmetic intensity, which is just dividing the number of operations by the number of bytes that are accessed. Here I am combining the floating point operations and integer operations because on the GPUs they are executed on the same CUDA cores or stream processors, and an integer operation typically blocks the core for the same clock for 1 clock cycle for floating point operations. So they are treated the same and simplified as flops here. So in this example, even though you might expect that it is compute bound because of the square root, and square roots might be slow, the arithmetic intensity is 0.5 flops per byte, which means it's bandwidth bound. I think, Giorgio, you have a question. Go ahead.
Okay, just the question about square root. For what I know, square root asks for more flops than single one. So the real arithmetic intensity that the GPU, the CPU, whatever you want, has to support is different.
Yes,
this is higher.
Not all flops are created equal. For example, a multiplication, floating point multiplication followed by an addition is compressed into a fused multiply add instruction that can compute the multiplication and the addition within a single clock cycle. So 2 floating point operations per clock cycle. For some operations, the square root, for example, the square root needs several clock cycles for the execution. Even worse examples are the trigonometric functions, for example, the arcus tangens hyperbolicus. This might need like 200 floating or 200 cycles, but it is still counted as a single floating point operation typically. However, the clock cycles per floating point operation can be different.
Yes, because if you compute this by hardware count, you find very strange different results, so can be a little bit misleading, which are the real roofline model that you have to follow. But thank you for the reply. Okay, go ahead. Thanks.
And it makes the analysis a bit more difficult because yeah, go ahead.
Det er det, du altid bruger. Nej, jeg ved ikke.
No question? Okay. Yeah, what I wanted to say is that it makes the roofline analysis a bit more difficult because the number of cycles per floating point operations, especially for the trigonometric functions, this is very different across GPU architectures. So the same code can take different amounts of clock cycles on different GPU hardware. But in this simplification, I'm just counting all operations as the same flops. And the counted flops from the code divided by the measured runtime will give you the performance in teraflops per second. So typically you measure it nowadays in teraflops, which is 10 to the power of 12 operations per second. These two properties, the arithmetic intensity and the performance, are plotted in an XY diagram, and this is known as the roofline diagram. For automatic counting of how many operations there are, I've open sourced a profiler. This works for the assembly code generated for Nvidia GPUs, which is the PTX assembly language. And it goes through the assembly code and it counts all of the arithmetic operations and the memory accesses and displays it all in a nice table for the roofline analysis. As an example, Fluidics 3D in version 0, in the roofline model, you see that so this was done on an Nvidia Titan XP GPU. For more details on the lattice Boltzmann algorithm, here it's D3Q19 with single, two, and multi-relaxation time collision operators from left to right. It's the one-step pull streaming implementation. Nowadays, I'm using the esoteric pull streaming, which is a different algorithm, so it changes things a bit. And I also counted the floating point operations and integer operations combined. Here, the different dots mean arithmetic and memory precision. So the first number, the FP32, is arithmetic precision, and the FP16 variants here, these are different formats for memory precision. So I compress numbers to a 16-bit floating point or even posit and store them in memory, but I don't do arithmetic in lower precision. Some more notes on these formats. So the FP16S is just IEEE format. The conversion runs in hardware. FP16C and P16, these are custom formats that need manual conversion, which takes about 50 clock or 50 instructions of bit shifting to convert the numbers from 32-bit floating point into these special formats. So for a single number that I write to memory, about 50 additional arithmetic instructions. And you see this in the roofline model. By default, the arithmetic intensity of the lattice Boltzmann method is about 2. So this is the leftmost point. And this is very far in the bandwidth limit. I should note that this slope curve, the white curve here, is the hardware limit. And the horizontal segment is the compute performance in teraflops per second, so about 12 teraflops per second for the Titan GPU. And the slanted part of the roofline is the memory bandwidth. And this is about 550 gigabytes per second for this GPU. And the points are measured from the arithmetic intensity of the algorithm and the measured runtime. I put the points in the diagram. And if they are located very close to the roofline, I know that the efficiency is already very good. So in this case, it's almost 100% efficiency. Now with this additional floating point compression, I need to do a lot more arithmetic operations. So the arithmetic intensity increases. I get more flops for every byte transferred to and from memory. Yet almost all of the dots still remain in the bandwidth limit, and only one for deposit conversion with the multi-relaxation time collision operator, only one is in the compute limit. And once you arrive in the compute limit, the performance is decreased. The bottom diagram shows sort of the same roofline model, but for 64-bit arithmetic. And for 64-bit arithmetic, the roofline is different for the hardware because the Nvidia Pascal GPUs only support 64-bit arithmetic with 1/32 of the performance of 32-bit arithmetic. So the floating point performance is greatly reduced. So the plateau of the roofline is much further down in the diagram, which also shifts the boundary between bandwidth and compute bound regimes to the left. And here the lattice Boltzmann method actually runs in the compute limitation. Now the measured points can never be above the roofline limit, because the roofline limit is the physical hardware limit. But you notice that in the bottom diagram, the dots are above the hardware limit. Why is that? The hardware limit here is from the data sheet, which says that the GPU clock frequency is 1582 megahertz. However, in the benchmark operation, because of dynamic GPU clock boost, the clock of the GPU cores increases up to 1800 megahertz. So the performance can actually be, the measured performance can actually be higher than what is specified in the data sheet, at least for the compute performance. The memory performance, not so much. Usually the bandwidth is really the hard limit here, unless you do tricks with caching. Now, OpenCL workgroups. So all threads are grouped in these so-called work groups, and threads within a workgroup can access the same shared or local memory, which is the L1 cache. The workgroup size is configurable, so you can, as a programmer, you can specify how many threads do you want in a workgroup. And it has to be a multiple of 32 for Nvidia GPUs or a multiple of 64 for AMD GPUs. If you set it to only 16 on an Nvidia GPU, for example, then half of the CUDA cores of each compute unit will just stay idle and not compute anything, while the other half does the computation. So you need at least 32 or 64 to use all of the hardware. If you don't use local memory explicitly, which is most cases, you can just choose the hardware default or 64. 64 is sort of large enough to saturate all hardware, to not cause any trouble with the too small or too large compute units. And it is small enough to have the workgroups individually scheduled. Now, register pressure. This is a bit more into the details of GPU computing. So all kernels can use variables, and any variable that you use in a kernel, like a temporary variable to compute some temporary result of an equation, for example, all of these are located in private memory space, which is the registers. And the variables take up registers in the compute unit, and the number of registers in compute units is limited. So typically the register size is a few kilobytes, maybe like up to 64 kilobytes nowadays. So the fewer variables you use in a kernel, the smaller is the so-called register pressure. And the more dormant workgroups can remain on a compute unit, waiting until the memory transaction is complete. So whenever you make a request for accessing global memory, typically the workgroup just gets paused on the compute unit, and another workgroup that already has memory gets processed first, and the other workgroup just sleeps until its own memory arrives. And several workgroups can remain dormant on the same compute unit. And the fewer variables you use, the more workgroups fit into the same compute unit, and the better hardware saturation you get. Usually, this is not really important for performance, just a thing to keep in mind. However, you can run into big problems if you completely ignore it. And if you have too many variables in the kernel, then at some point the workgroup, even a single workgroup, does not fit in the compute unit's registers anymore. And it is still executed, so the code still works, but the part that does not fit is spilled into either cache or video memory. So this spillover into the slower parts of memory creates a very large performance penalty. As an example, here is Fluidix 3D version 0 on a Nvidia Tesla V100 GPU. And what was particularly interesting about the Volta architecture was that if I do the multiple relaxation time collision operator, which does a larger matrix multiplication entirely in registers, so either a 19 by 19 or 27 by 27 matrix multiplication, then I run into a register spill problem. So the large matrices do not fit into the registers of the V100 anymore. On other GPUs, I didn't notice this problem. So this was really particularly interesting that it only happened on Nvidia Volta. And while all of the other points are perfectly on the roofline model with 100% efficiency, the dots for the register spill are way further down. So the performance is really bad for these two cases. Now a very famous optimization, the so-called cache tiling or local or also shared memory optimization. What is the idea behind it? So for each thread in a workgroup, you load only one value from global memory in a coalesced memory access. The VRAM access is very slow. The latency is between 400 and 800 clock cycles. So you load global memory to local memory, and one thread does only one single value. And then all of the threads in the workgroup can access all of the values from local memory. So anyone can access all of the others. I've indicated this with all of the arrows, but it was just too many arrows to draw them all. And yeah, this access is a lot faster. And this is useful in cases where you want to access several global memory values from the same thread, but you access the same elements across threads in the workgroup. So overall, you have much less global memory access, and this can greatly speed up performance. Now, on to another interesting topic for high performance computing. I've told you before that the video memory capacity is very limited on GPUs. And to sort of go around the problem, you want to use more GPUs. More GPUs, more better. So just use several GPUs at the same time, but it's quite difficult because you have to do the parallelization and the data transfer between GPUs manually. Here, this is one example how I do it in Fluidix 3D with a domain decomposition approach. So Fluidix 3D is a lattice-based, lattice-Boltzmann-based CFD solver. It works on a Cartesian grid, and I can split a Cartesian box in the middle in two boxes and compute the left box on GPU 0 or GPU 1 and the right box on the other GPU. And between the domains, there's the boundary, and across the boundary, some data has to be transferred. It's not a lot, but some data transfer has to happen in every time step. And the way I do is, I allocate a so-called transfer buffer on the GPU, and while the domain itself is many gigabytes in size, this transfer buffer is only really for one surface, and this is only a few megabytes in size, so very small. With a custom kernel, I copy the data within video memory from the domain in this transfer buffer. I do this at both GPUs, on both GPUs at the same time. And over the PCI Express bus, I copy the data into transfer buffers on the CPU side. And then the smart thing is that I switch the pointers on the CPU side. So the CPU does not have to copy any memory around, it just switches the pointers to the arrays. And then I can copy the data back from CPU to GPU to the transfer buffers, and from the transfer buffers back into the domains. The nice thing here is that this works cross-vendor, so you can sort of SLI together an Nvidia GPU and an AMD GPU and an Intel GPU at the same time. You're not bound to any specific vendor. There's only a single GPU transfer buffers, so the additional video memory requirements are very low, only a few megabytes for these buffers. The disadvantages are that it only works across a single node because there's no MPI communication in between. And the data transfer between the CPU and the GPU over PCI Express is really slow. So the bandwidth of PCI Express is nowadays about 32 gigabytes per second peak, which is not too much compared to 500 or even 1,000 gigabytes per second of video memory bandwidth. To scale this to multi-GPU, I can sketch out the chart here. So I need to modify it a little bit and add a second buffer on the CPU side. So split it into a send and a receive buffer. So the data gets at first the same way sent into the CPU buffer, but in the send buffers. And then I do an MPI copy from the send to the opposite receive buffer, and from the receive buffer back onto the GPU side again. So the advantages are it works across nodes, so for multi-node parallelization. It's also cross-vendor compatible, and it still only needs single GPU transfer buffers. The disadvantages, again, you need slow PCI Express copy, and additionally slow memory copy between CPU nodes even, but you cannot avoid that. And MPI also might not always be available on all systems. It's available on all of the supercomputers, of course, but if you deploy the same software on a personal computer, the user might not have MPI installed. So you need to make it switchable with a macro in the code, and that can get very messy. Now, the sort of ideal approach to multi-GPU communication is with so-called GPU-aware MPI. So in this case, you need duplicate transfer buffers on the GPU side, but you can, with MPI, directly copy the memory from one GPU buffer to a different GPU buffer directly over the network. And ideally, this would use the fast interconnects, NVLink, SLI, or Infinity Fabric. So it is potentially faster, potentially even a lot faster. It works across multiple nodes, but it does not work with OpenCL. And this is sort of the biggest disadvantage for OpenCL that I have found so far, that GPU-aware MPI just does not work. It is not supported by any of the vendors. Other cons are that you need duplicate GPU transfer buffers, so a bit more video memory allocation, and of course MPI also might not always be available, but it doesn't work on OpenCL, and so you can really forget about this approach. It's not portable. Now, another trick that I want to give you on hand, you can use the OpenCL queue to enqueue kernels on different devices, because excuse me, do you have a question? Go ahead. Okay, no question. Yeah, you can enqueue kernels on several GPUs at the same time, and because the enqueuing is non-blocking, it gets computed almost instantly. So all of the kernels, all of the GPUs start really at the same time, and then you can make another loop with the queue finish command, and this is blocking. It waits for all of the GPUs to finish, so it waits until the slowest one of all of them is done. And this way, you don't need OpenMP or the threads library or the concurrency parallel for library. You can just use a single C++ thread, and this is actually faster than any of the other approaches. So just a very elegant trick that I want to give you on hand. Now onto a small case study. I am not doing the boring matrix multiplication with you today, but I am doing the GPU voxelization of a triangle mesh. So this is an example of the Concorde airplane, and I use an algorithm to load a triangle mesh from an STL file, and I voxelize it for the simulation. So I mark all of the voxels that are inside the mesh. So how does the algorithm work? The brute force algorithm, which has a runtime of n cubed times, so n is the side length of the box times the number of triangles. The idea is that from each grid cell, you shoot a ray out in some direction, and you count the number of intersections with the triangle mesh. You do this only within the bounding box of the triangle mesh. So there's already a quite big optimization. And you check each of the rays for the intersections with all triangles. And if the number of intersections is odd, you know that it is a solid cell. So if it's only one intersection, if it's inside, but it also might be 3 intersections and it is still inside the mesh. And then you can mark the cell as a solid cell. I can also optimize this with the local memory optimization. The idea here is to load 64 triangles at a time into local memory, and then for all of the rays in the workgroup, access all of these 64 triangles at the same time, and then continue on with the next batch of triangles. And this already improves performance. So here is the runtime of these two variants. So the brute force variant takes about 4 minutes, and the local memory optimization reduces runtime by 30 seconds to 3 minutes and 30 seconds, which is quite a good optimization already. Now let me tell you about the really optimized version, which has a runtime that is so fast that you don't even see the bars on the chart. Sub 1 second runtime. The way I do this is to use a smarter algorithm, which has a runtime only proportional to n squared times the number of triangles. So the idea is only for the bottom layer of the cells in the bounding box, for the smallest cross-section area of the bounding box, I shoot rays vertically upwards, and the rays are axis aligned with the grid, so they pass through all of the grid points that are located above the bottom layer. I keep track of all of the intersections along the ray. I sort the intersections by distance, and then I march along each of the rays and switch between solid and fluid state at each intersection. I can also do the local memory optimization for this algorithm. So also for all of the rays, the same way as above, load 64 triangles at a time in local memory and access them with all threads, and then continue with the next batch and so on. Yeah, and the runtime is 3 orders of magnitudes faster than the brute force version. And the local memory optimization speeds it up even further to about 1/6 of a second, which is super fast. So this is quite a large domain already, 220 million cells, and the mesh has 142,000 triangles. And yeah, this is great that it runs so fast, because this means I can voxelize even moving geometry in between time steps. And the runtime is so quick that, for example, for rotating geometry.
Yeah, well, from say I am not going to divide the whole team, no, for every meeting at the end of the day. Well, the main point of contacts, no, with the team is going to be, okay. For sure, you can directly contact them, whatever, okay, but please include that, no independent communication, just be aware of that. We were talking, no, Isabel, if we need to think about some kind of replacement from the wave 1 to this wave 1.5.
Excuse me, I couldn't understand the question. Yeah, so the runtime is super fast, and it's fast enough to do voxelization steps in between time steps without impacting the overall runtime too much. To show you the code, and that you have at least once have seen how the local memory optimization works, here's the relevant part in the voxelization algorithm. So the first part here is I need to check for the entire work group if any of the work groups is in the bounding box of the mesh, and then I need to execute the remaining part. If none of the work groups is in the bounding box, I can just return. So this first part just exits for all threads that are outside of the mesh bounding box. Then comes the actual local memory optimization. So I make small arrays of the triangle points, P0, P1, and P2, each of size 64. So this def underscore workgroup underscore size is a macro for the number 64. And then I do two nested loops. The outer loop goes over all of the triangles, and it increments the index by the workgroup size by 64. The first part here is loading the values from global memory into local memory. And here there's an if condition around that, because in case the global memory index is out of bounds of the array index, I will get an out of bounds memory access, and this can crash the program. So I need this, this condition here. Then comes a barrier, which means that all threads in the workgroup have finished with the first part, and the global memory is now full with valid data. Now comes the inner loop. Here I iterate only across the workgroup size, so only for all of the threads index 0 to 63. And I access the cache data from local memory. I do the intersection computation. And after the inner loop, I do another barrier to tell the compiler that now the first iteration is finished, and the cache, the local memory, can be overwritten for the next iteration. Here in the inner loop, you also need to pay attention to add a second condition, such that the access index for the local memory is not larger than the triangle number in this case, which also would lead to an out of bounds memory access violation, which can crash the program. So keep in mind that the array size might not always be a multiple of the workgroup size that you choose. And either you do it with sort of a guard clause or extra conditions, or you add buffering, so some buffer zeros to the memory buffer to make it equally divisible and not have the out of bounds access violation bugs. Now, to conclude, I will provide you with some final tips for writing your own OpenCL software in case you run into problems with performance. So the first and most important tip is to work smart, not hard. The largest performance gains don't come from faster hardware and brute force, but from optimizing algorithms. And with a smarter algorithm, you have seen it in the case study, you can optimize performance by 3 orders of magnitude. Avoid memory allocation and deallocation. Only do this once in the beginning and then reuse the memory all over again in every time step, because memory allocation is super slow. On the GPU, it's all or nothing. So the best way is to just implement everything on the GPU, because this allows you to avoid CPU and GPU data transfers within simulation time steps. If you have to do these large PCI Express data transfers between time steps, then the transfer time makes the overall application slower than if you would just have used the CPU alone. So either put all on the GPU or just leave it, because data transfer is super slow. There's a nice example, the Espresso software that our own work group has worked with and also implemented a red blood cell model with. So we simulated blood flow through a microcapillary where individual red blood cells, they look a bit like donuts, were moving through a rectangular channel and deforming along the way. And the fluid model is Lattice-Boltzmann, and there's an additional model for the cell mechanics of the cell membrane. And in the Espresso code that our university workgroup has modified, the GPU the fluid solver was implemented on the GPU and really fast, but the membrane mechanics of the cell was implemented on the CPU. So in between time steps, you had to copy the entire velocity data field between GPU and CPU to do the cell membrane model on the CPU, and then copy the cell vertex positions back to the GPU again. And I've implemented this in our internal fluidics 3D version, the cell membrane mechanics, and run the same benchmark on the same GPU hardware, and it was faster by a factor 20. So avoiding data transfer can bring you a long way for performance. Then find out the arithmetic intensity of the algorithm. This will let you know if it is bandwidth or compute limited. In most cases nowadays, the algorithms are bandwidth limited because the sort of kink in the roofline curve for the modern GPUs is at 80 flops per byte. So if you do any less than 80 floating point operations for any byte that you load or store in memory, you are already in the bandwidth limit. Just be aware of that. The structure of arrays memory layout is critical for performance because this allows you coalesced memory access. Just by changing the memory layout, you can get an easy factor of 3 to 5 in performance, going from misaligned to coalesced memory access. Now also know when the local or shared memory optimization is useful and when it is not, because this optimization sometimes is not really beneficial. Because, for example, when you have your work group and each one accesses one element of data but needs to access the neighbors left and right, it means that the elements on the leftmost and rightmost side of the work group need to access additional elements from global memory. And this creates branching again and can then be slower or no performance benefit at all. But for some applications, for example, the voxelization algorithm, there's a decent performance uplift. And for matrix multiplication, for example, the performance benefit for cache tiling is even larger. Keep an eye out for register spills. Just using too many variables is bad, and you might not notice it until it's too late. And never trust the compiler to optimize anything for you. I'm very skeptical of the compiler and just optimize things by hand, because then I can be sure that the compiler does not do any weird things. And as a final point, 64-bit arithmetic avoided if possible, because on almost all of the GPUs nowadays, it is only supported with 1/32 or even 1/64 ratio to 32 with floating point. So it's very, very slow. It's only fast on the super high-end data center GPUs like the Nvidia A100 or the AMD Instinct accelerators. Even some of the Instinct GPUs don't support or support FP64 only with lower precision. That's the ones based on the gaming models. And the gaming and the workstation GPUs have the same poor FP6 performance nowadays because they have identical silicon. They only differ in memory capacity sometimes. So be aware that 64-bit arithmetic can make the code super slow. And sometimes in some applications, like the very first one that I've showed you, this N-body simulation of the solar system, this was one of the few applications where 32-bit floating point is not enough, because computing all of the forces between the planets can do digit extinction effects, and you need really all of the 16 digits. And for this application, I needed 64-bit floating point precision. And for these cases, like simulating the solar system using a GPU is not beneficial, because it's just faster on the CPU in C++ code, because the CPU can do FP64 at very high performance. All right, that was it from my side. Thank you for your attention. And I'm happy to take any questions and discuss with you.
Okay, thanks very much, Moritz. I have a question for you about CUDA awareness support from OpenCL. I think this is a very big limitation, especially for big simulation, if you want to use OpenCL. Have you an idea the reason why there is no support for CUDA awareness? Do you think it will be done in the near future, or there is some reason not to do the CUDA, the GPU support for CUDA or similar awareness of MPI?
Yeah, this is really up to Nvidia what they do. So there's not really any technical difficulties. It's purely a marketing decision to keep the users on their own CUDA platform, but there's no technical limitation to make or to enable GPU aware MPI also for OpenCL.
Okay, but
I hope they will do it, but I'm not sure if they ever will. So I'm asking them over and over again, but there was no response so far.
Okay, but the other vendor, namely AMD or Intel, they will support this one in the near future, or for the same marketing reason they don't like? What is your feeling?
I think AMD is closer to supporting it because they can do shared virtual memory, and they also have the peer-to-peer copy commands already in their API, even though they do not yet work. But I hope they implement it in the future.
Okay, so probably the first will move to a sort of awareness, will not win, but will set the pace, in my opinion.
I hope Intel will also support it for their Ponte Vecchio and Arc GPUs.
But have you tried to run on Ponte Vecchio?
Not yet. I didn't yet have access. The Intel Developer Cloud is just providing access to the first users, and I'm looking forward to test it eventually. But I haven't yet tested it. I've only had a friend test it on 2 Intel Arc GPUs, and there it is not supported at all, which is expected because for the Intel Arc drivers, there's still larger construction sizes that need to be fixed.
Okay, thanks.
All right, Iris, go ahead.
Hi, Moritz.
Hi.
Thank you very much for the talk, actually. I was wondering if you ever compared your OpenCL version against CUDA performance, a proper CUDA code. Have you tried this, or did you stick with OpenCL to be portable?
I mean, you've seen the roofline diagram, and you've seen that the points are exactly on the roofline. So there's just no possibility to make it any faster. I've seen some other codes. For example, Valberla is also one of the latest Boltzmann GPU codes, and they have very similar performance in CUDA, so they are just as fast as OpenCL. But since I know that I'm already at 100% memory bandwidth peak, I know that there's no disadvantage of using OpenCL, and I don't even make myself the effort of testing out CUDA because there's just no reason to use it, because OpenCL offers so much better compatibility.
And maybe a second follow-up question. So how good is the portability? So if you switch to a different cluster with different GPUs, how much effort do you have to put into your code to get again?
Okay. I give you an honest answer on that. So ideally, OpenCL promises to be perfectly portable, and in most cases it is. And if you pay really great attention on writing the code and avoid all of the pitfalls, you can achieve perfect portability. The Fluidics 3D software, it runs really on any GPU, but only because I have avoided all of the mines. Because if you dig into OpenCL really deep, you will see that at some point it becomes a minefield of driver bugs. But this is really deep into the details. And for example, on old AMD GPUs, so the first and second GCN architectures, if you put a binary integer literal, so in the binary notation 0B and then all of the bits as zeros and ones, it won't work. It will crash the compiler, and you have to write it as hexadecimal literals instead. And it won't get fixed by AMD because the drivers are already legacy. So there's certain pitfalls and certain driver issues that you have to avoid. I'm already working with the GPU vendors whenever I find a bug. For example, I found once in the Intel GPU drivers a bug that the length of the float 3, so the 3-component vector, was actually a 4-component vector by the compiler, and it created issues. But Intel fixed this already. And for Nvidia, it's similar things. There's sometimes bugs in the drivers. I've already reported a few, and usually they come back to me within a few days, and it takes maybe a few weeks to months for them to fix them, but they really do fix them, and they put great effort into fixing driver bugs. And yeah, in the ideal case, then once you avoid all of the pitfalls, you can actually achieve perfect portability.
Okay, thank you very much. That sounds actually very promising, I would say.
I have a little comment. In the roofline model, sometimes I found, especially for lattice Boltzmann simulation, more useful to express not the megaflop in terms of computational intensity, but the mega loops, the million lap case, because in this way is hidden how many flop I have to perform to complete a lattice update. That can be a number, can change. I can write in a particular way, so to make an abuse of floating point operation or useless classical operation. For example, computing velocity, you can do one simple sum or many multiplication for 0, 1 that counts as a floating point operation, but are waste of time. So and just a comment. This can also be used to make a fair comparison between different applications, in which you have an information of the time to solution to solve a particular test case with similar complexity of the code, so the same time relaxation and so on, but it's more plain. Flops are a metric that can be sometimes misleading, in my opinion.
Yes, that's a very good remark. So for all of the others, mega loops means million lattice cell updates per second. This is a specific performance unit for lattice Boltzmann codes. So how many million cells are updated per second? And lattice Boltzmann scales performance with the memory bandwidth. So in the roofline model, performance scales perpendicular to the slanted part here, so directly with the memory bandwidth and not with the vertical axis. And by annotating this as the mega loops performance, you show that it scales at firstly with the diagonal, and the second thing is that between different codes, the algorithms might be somewhat different in the details, and the number of floating point operations and also the number of memory transfers can be different between algorithms. And the mega lattice updates per second just give you the absolute performance number, so it's a better unit for comparison. And it will at the same time, so in the mega lattice updates units, you can of course also plot the hardware limit with the memory bandwidth. You can directly convert that to a mega lattice updates units limit. So it's just putting a different unit on the axis here.
No. Thanks.
Any further questions?
I had a question. First of all, very, very nice presentation. The question is about loading global memory to local memory. And because in my concern, I'm starting to dig into OpenCL and GPU programming. And one thing it was not clear to me is how to optimally do this local loading. Let's suppose we have n work groups, and each work group works on a coalesced partition of a global memory, of a global array. So you just load once that slice in the local workgroup memory, and then each thread inside the workgroup does something on each element, let's suppose. How to optimally do it, like in code? Like you just declare a local variable? How do you do it in practically? That's the question.
I can show it to you in the example again. So you declare these local variables. They can be any of the supported data types. They have to be in static allocation because dynamic allocation is not supported. And it only works in the kernel directly. You cannot put local variables in functions that are then called by the kernel. Sure. This worked with the previous Nvidia driver with their older compiler, but they recently changed compiler or upgraded the compiler actually to a newer version, which is more strict with the specification and doesn't allow local memory in functions anymore. So it only works within the kernel directly. So you sort of have to manually inline the inline function code. And yeah, the way to do it is to just allocate, I don't know if you see my
yeah, I do see.
Okay, you see my mouse cursor, good.
Yeah.
So you just make local variables with the local keyword. If there's no local keyword, any other variables here are just private memory. So the local keyword makes it a shared memory variable. And then you have a larger loop that goes over batches of the workgroup size. And within each iteration, you load one element for one thread. In this case, it's 3 because it's 3 points in the triangle and I need to load all 3 of them. And this is coalesce access because consecutive threads access consecutive global IDs for these points in the triangles. And the local memory gets filled this way. Then you need a barrier, a local mem fence, to make sure that all of the threads have filled their own portion of local memory and that the entire segment of local memory is valid data. And then you do a smaller loop that only iterates over the workgroup itself. And within this, you can then load the local memory into a private memory, which I do here in this line. And then you can do a bunch of computations on private memory. And once you're finished, you need to do another barrier for another local memfence barrier, because after this one, new values are written in local memory. If you leave this out here, then some threads might still compute here, while other threads might already override the data in local memory, and you get a race condition bug actually. So this is the way to do it.
Okay, so you need to fill it manually, like for each work group,
yes.
You have to fill it manually. Okay, thanks. And a last question, another question, if anybody else doesn't have, if I have just 1 minute more, I don't know.
Yeah, go ahead. We have time.
You show some very nice benchmarks. And how do you suggest to properly benchmark an OpenCL code? Because, for example, Nvidia has inside compute and systems technologies, which might help you like debugging and profiling. Like, what is your suggestion with OpenCL kernels and OpenCL aware code to profile it?
So there's some very nice tools from Intel. They have in their one API a very nice profiler. But I myself have not used any profilers at all in the entire time that I've worked with OpenCL. What I do instead is I just measure the execution time of a kernel up to the nanosecond, or even if it's too short, I make a loop across maybe 100 or 1,000 iterations of the kernel to get very accurate average time measurements. And within the kernel itself, I just try different variants. I might comment out parts of the kernel code to see which part really hits the performance. And then I also look into the PTX assembly code. I have this PTX profiler tool that counts the flops and the bytes and transfer for the roofline model. And this counts the flops for the different floating point types already. So for 64 and 32-bit. And I can already spot if something goes wrong. For example, if you don't specify a floating point variable with the lowercase f in the end, it is a double variable in double precision. And if you have a longer equation with one of these double literals in it, it will, if not enclosed by brackets, all of the other variables will be implicitly converted to double precision, and the equation will be computed as double precision, and the result is then again converted to single precision. And if you miss such things, it can really hurt performance. So just a single character at the end of the floating point literal can give you really bad performance. And this PTX profiler tool tells me whenever there is some 64-bit floating point operations present, I immediately notice this.
Okay, thank you. Thank you for the answers. Thanks a lot.
Yeah, Francesco, go ahead.
Hi, Moritz. Thanks for the very, very interesting presentation. I have a quick question about the data race or race condition you mentioned.
Mm-hmm.
Do you have any specific remedy for that? I mean, do you use some sort of equivalent of mutex on GPUs as well?
There is no mutex in OpenCL, unfortunately. Where is the race condition? There it is. So you cannot use mutexes. They are too complicated for GPU hardware. On a CPU, you can do it, and I'm also using atomic variables and mutexes on CPUs for multi-threading. It's the common way to do it. On the GPU, there's special instructions. These are the atomic instructions. And atomic means that whenever one thread accesses the memory cell, it blocks the memory cell for any other thread to access. And this way you can avoid race conditions. Typically, this is used for integer arithmetic and integer variables. For example, you can have a counter variable in a memory cell and then have several threads increment the counter. And the order doesn't matter because integer addition is errorless. And you don't lose any of the increment from any of the threads because the atomic operations block the cell for one thread at a time. So atomic operations is the way to do it on the GPU.
Okay, thank you very
for
much.
synchronization, I might add, you cannot put like thread synchronization blocks within a kernel. Although you have seen these local synchronization barriers here in this example, but they are only synchronization barriers for the workgroup itself, not synchronization across workgroups. If you need to synchronize across the entire data array, across all workgroups, then you need to close the kernel and start another kernel. So you need to separate the kernel in two kernels. And too much separation in kernels can create overhead. This is a bit illustrated in this diagram here because each kernel can have a bit of a different runtime. And if they are very slow, the differences in runtime relatively can be quite large. And the synchronization barrier always waits for the longest runtime. The kernels themselves also have a launch latency. So ideally, you want to minimize the number of kernels as far as possible. But sometimes you just need the synchronization barriers.
Okay, thanks very much.
Any further questions?
Seems no other question. Then Varvara confirmed that every attendee will receive a link for a simple questionnaire to understand the quality and which argument can be exploited for this webinar. So if there is no other question, I'd like to thank very much Moritz for his very deep and complete description of his work. I hope the information can be useful, and the slide and also the registration will be available soon. Give us some technical time to set up all the machinery. So I have nothing else to say.
Also from my side, thank you very much everyone for attending. Thank you for the great interest in OpenCL. It is a fantastic language, and I hope to increase the popularity of OpenCL for more different use cases, because I really think that it is the best language for GPU programming. Thank you very much.
Okay, thank you very much. And because it's quite near to July, I hope you enjoy your holidays, and keep in touch that in the ChEESE framework we'll make other webinar about programming, and especially around performance portability, so GPU and different tools. Thank you very much, and see you the next webinar. Bye.
Bye-bye.